The inverse function theorem is the topic of this clip, and let me start by motivating. What do we want to do? So suppose we have a system of equations as follows. So it's going to be y1 is going to be a function, let's call it f1, of n variables, x1 up to xn. And y2 is going to be a function, call it f2, of x1 up to xn. And in total, we're going to have exactly n of these. Yn is going to be a function, fn, of x1 up to xn. And as usual, we're going to assume that for every I, let me not write it here because I want to use this space. So for every I, fi is a C1 function. Okay, so all the partials are nice and continuous. And so this is the situation. Now, before saying what we want to do, let's think of the situation where where n equals 1. When n equals 1, well, when n equals 0, it's boring, there's nothing here. But when n equals 1, there's only one equation like this, right? There's only one y, let's call it y. There's only one f, let's call it f. And there's only one x, let's call it x. Do you agree? Yes.
So the n's are the same?
Yeah. When I'm using the same letter, it's the same letter. Okay? So suppose we only have one n equals 1. So we only have y equals f of x. Okay, wait. Y equals f of x. The question I want to ask, hinted by the title of this clip, is when can I write x as a function of y? When can I have an inverse function? So for example, if y equals e to the x, then I know that x equals ln of y. Do you agree? If y equals x squared, then x equals the root of y, right? Well, there are always domain issues, right? You have to be a one-to-one function in order for the inverse to exist. But that's what I'm trying to generalize now. So I have all these y's, n of them, expressed as n functions of the n variables x's. Question is, when can I write the xi's as functions of the yi's? Clear? Okay, so let's write it. When is not today, tomorrow, later, or previously. When is under what conditions? Under what conditions can we write the xi's as functions of the yi's? That's the question we want to tackle. That's the inverse. Okay, clear? Okay. Now, the way to tackle this question is to set this up into the setup of the implicit function theorem. The implicit function theorem told us when we can write certain variables as functions of the other variables. So that's what I want to do. So let's rewrite this thing in the following way. Let's introduce new functions. We're going to use capital F for them. These are going to be relations between all the variables. So f1 is going to be a function of y1 up to yn and x1 up to xn. A function of all these variables. And it's going to be defined as little f1 of x1, x2 up to xn minus y1. That's the definition of capital F1. And similarly, f2 of all these equals f2 of the x's, little f, minus y2, and likewise all the way up to fn. Make sure you distinguish between big F's and little f's. so you don't get things totally confused. Okay? Now, do you agree that since we know that these little f's are C1 functions, so are the big F's? Do you agree? Okay. Now, let's recall the implicit function theorem for systems of equations. In the implicit function theorems, we had the variables, which are here called y's, but those were called x's in that theorem. And then we had these variables, which are here called x's, but were called z's in that theorem, in the previous clip, right? And the theorem told us when we can express the z's as a function of the x's. Remember? So that's precisely the question we're asking right now. When can we express these variables, now called x's, in terms of these variables, now called y's? Do you agree? So the implicit function theorem gives us a precise condition when that can be done. It's that determinant with the partial derivatives that has to be non-zero. Remember that? Okay. So the question which we just asked, when can we express the x's as functions of the y's, is precisely exactly the question, when does the implicit function theorem hold for this system? Okay, is answered by the implicit function theorem for systems. It boils down to precisely that. When is that big determinant corresponding to this, taking the derivatives of all these big f's with respect to the z variables, when is that determinant? Not zero. Do you agree? Okay. We need that determinant. So what was the determinant? The derivatives of the f's with respect to the z variables, which are now the x's, right? We need that, what we called delta previously, but it's now the determinant. The determinant of what? Of df1 to dx1 up to df1 to dxn, and down here up to dfn to dx1 and dfn to dxn. We need that this be not zero. Do you agree? Yes.
Why is there a yn inside the bracket in the f1?
I'm defining a new function, yeah, f1, as a function of 2n variables. Okay? Now, you're asking, wait, but f1 does not depend on yn, right? Is that what you're asking? It only depends on the xn's and on y1.
Yeah, so why is there an yn?
Well, if I write a function, f of xy, is this a legitimate function? But it only depends on x. Okay? So it's legitimate to have a function of several variables, which is fixed with respect to some of them. Okay? But in order to fit in the framework of the theorem, it's important that all these functions are, in general, functions of all the variables, and then it allows me to use the theorem, the implicit function theorem for systems. Okay? True, fi does not depend on the y's except for yi. Okay? But nevertheless, it's going to allow me to write all these x's as functions of all these y's, because it's a system. They're all, these relations in total apply to everything together. Okay, clear? Okay. So let's figure out what this determinant is. What is the derivative of f1 with respect to x1? Here's f1. This is f1. So what's the derivative of f1 with respect to x1? It's precisely the same as the derivative of little f1 with respect to x1. Do you agree? So this determinant becomes, so remember, our original question didn't have these big f's in it, right? It only had the little f's. Let's look a board back. This was our original question. When can we write the x's as functions of y's, right? The answer is you need the determinant of these f functions that are in the data with respect to these variables, okay? So let's write that. Looking again here, we need this determinant to be non-zero. Therefore, thus, the condition is that the determinant of the matrix d little f1 to dx1 up to d little fn to dx1, d little fn, sorry, made a big mess here, df1 to dxn, and then dfn to dx1 up to dfn to dxn. This determinant has to be non-zero. Do you agree? Good? And if this holds, then we know by the implicit function theorem, we can invert the entire system. We can write, do we have the formulas for the inverse functions? No. We just know it can be done. Okay? Okay, we don't have the formulas, we know it's achievable. Okay? And this thing has a name. Okay? This determinant is let's write it differently. Notation. This determinant is written as d f1, f2 up to fn over d x1, x2 up to xn. This is just notation for this n by n matrix, its determinant. Okay? And it also has a name. So this is this, called the Jacobian. The Jacobian of the system, of this system of equations, y1 equals f of x1 up to xn, and up to yn equals fn of x1 to xn, called the Jacobian. Okay? And another notation is sometimes you'll see j or j of f, or all of these are different notations for the same thing, the Jacobian. Okay? So the Jacobian is something very tangible. It's just a calculation of partial derivatives, which we have to evaluate at the point at which we're interested, right? This is the function form. We have to evaluate it at specific points in order to know if we can find an inverse in the neighborhood of that point. And we're going to use this Jacobian throughout. In many, many different cases, we're going to see that the Jacobian plays a role. Okay? So in this theorem, it told us, but we didn't write the theorem, right? So the theorem is that the answer to the question is, if the Jacobian is not zero, then we can invert the system. Okay? So maybe let's write that. So the theorem, the inverse function theorem, if j is not zero, I'm really writing it very unformally, because you have to state, if you want to write the theorem formally, you have to say, consider the system of equations, y1 equals f1 of x1 up to xn, y2 equals f2 of, write the entire system. And assume that all the fi's are C1 functions. And assume that the Jacobian of the system, given by this, is not 0 at a point, pa-pa-pam. Then we can invert the system. We can write the xi's as functions of the yi's. Then there exist functions x1 equals, let's call them g1 of y1 up to yn, x2 equals g2 of y2 of y1 up to yn, etc. Okay, so I'm not going to write all of that. I'll just be brief. If j is not 0, then there exist, you know this symbol, right? There exist functions xi equals gi of y1 up to yn. We can invert the system. These functions are unique, and they're C1. In a neighborhood, bum, 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 bum. Clear? Good? Okay. So, good. So this wraps up our discussion of the implicit function theorem and its consequences and uses. And we'll get back to this. We'll see the Jacobian again when we talk about integrals. That will follow a bit later. Okay, so let's have a 5-minute break.